Welcome to The Explainer. Today, we're going to dive deep into the one piece of tech that basically powers all the modern AI you hear about, from ChatGPT to all the incredible translation tools. It's called the Transformer. And honestly, if you want to understand the AI revolution, you've got to understand this.
So let's start with a really big question. When you type something into an AI, how does it actually get what you mean? How does it understand the nuance, the context, all the little connections between words? It's not magic, I promise you. It's just a really, really brilliant piece of engineering.
And that answer, the key to all of this, is the Transformer. It all started with this landmark paper back in 2017 from some researchers at Google. The title was kind of bold: Attention is all you need. And you know what? They were right. It completely changed the game.
So why do we call it the engine of the AI revolution? Well, it all comes down to one absolutely massive breakthrough that just changed everything. And that breakthrough is all about one thing: speed.
The number one benefit here is just insane speed, and it gets that through something called parallelization. See, before the Transformer, you had models that had to read a sentence one word at a time, in order, super slow. The Transformer, it looks at the entire sentence at the exact same time. This was a huge leap forward, and it slashed the time it takes to train these giant AI models. It's the reason today's AI can be so big, so powerful, and so quick.
All right, let's imagine the Transformer is a machine designed for one job. Let's say translating French to English. What's actually going on inside that machine? You know, from the outside, it's pretty simple. It's just a black box. You feed it a sentence in one language, and out comes the translation. Easy enough. But the real magic, the really cool stuff, happens when we pop the hood.
So when we open it up, what do we see? Two main sections. First, you've got a stack of things called encoders. Their whole job is to read the sentence you gave it and just understand it. Then you've got a stack of decoders, and they take that understanding and start building the new sentence in the other language.
But hold on, how does an encoder understand anything? Well, this is the secret ingredient. This is the core idea from that paper I mentioned. It's a mechanism called self-attention.
Let's use a sentence to see how it works. Okay, picture this. The animal didn't cross the street because it was too tired.
Now, for you and me, this is a no-brainer, right? It is the animal. But for a computer program, this is a classic problem. How does it know that it refers to animal and not the word that's closer, street? That's actually a really tough challenge.
And this is precisely what self-attention was built to solve. As the model is looking at the word it, the self-attention mechanism lets it look back at all the other words in the sentence and basically score how relevant each of them is. It figures out how to draw this super strong line between it and animal, essentially baking that context right into its understanding of the word.
Okay, so how does it actually calculate all of this? This is where things get really clever. It's a surprisingly elegant process that uses a few core ideas.
For every single word that goes in, the model creates 3 different little packages of information, or vectors. They're called query, key, and value. The easiest way to think about it is like this. The query is the current word asking a question like, hey, who in this sentence was tired? The key from every other word is like a label on a folder that says I'm a noun, or I'm a potential answer. And the value is the actual stuff inside that folder, the real substance of the word. Okay, so here's the magic recipe, step by step. First, like we said, it makes those query, key, and value vectors for every word. Then the model takes the query from the word it's focusing on and compares it to the key of every other word to get a score. After a little bit of math to keep the numbers from getting weird, it uses this function called softmax that turns all those scores into nice, clean percentages that add up to 100%. Those percentages are the attention weights. They tell the model exactly how much attention to pay to every other word. Finally, it takes those percentages, multiplies them by each word's value vector, and adds it all together. What comes out is a new representation of our original word, but now it's supercharged with all this rich context from the rest of the sentence.
But wait, it gets even cooler. The model doesn't just do all of that one time. In the original paper, they suggested doing this whole process 8 times, all at the exact same time.
This is what's known as multi-head attention. Think of it like reading the same sentence 8 times at once, but each time you're wearing a different pair of glasses. One pair might help you spot the subject and verb. Another might focus on pronouns. A third could look for cause and effect. It gives the model this incredibly rich, multi-layered understanding of the sentence all in one go.
All right, we've got our core mechanism, this amazing self-attention thing.
But there's one last absolutely crucial piece of the puzzle we need to talk about: word order.
So remember how we said the transformer looks at all the words at once? Well, there's a small problem with that. It means the model itself has no idea which word comes first, second, or last. To fix this, we add a little extra piece of information to each word called a positional encoding. It's basically a little tag that tells the model, hey, I'm the first word in the sentence, or I'm the fifth word, and so on.
And yeah, this is exactly why that's so critical. Without knowing the order of the words, meaning just completely evaporates. You just get, well, gibberish. Positional encoding makes sure the model can keep track of the sequence, even while it's processing everything at once.
So when you put it all together, you've got the encoders and decoders, you've got the incredible power of multi-head self-attention, and you have positional encoding keeping everything in order. You don't just get a slightly better AI, you get a complete and total paradigm shift.
So look, the big takeaway here is that the transformer wasn't just a small tweak. Its ability to process words in parallel meant we could suddenly train models on massive amounts of data. Its self-attention gave it a way to understand context, even in really long, complicated sentences, better than anything before it. And because of those two things, it became the fundamental blueprint for pretty much every single large language model we talk about today.
By giving machines this incredible new way to understand the ridiculously complex relationships in human language, the transformer just blew the doors open for a whole new era of AI. And that just leaves you wondering, right? Now that our machines have this deep, powerful sense of context for language, what will we ask them to understand?